Students, the sun is visible to us about 2 minutes before the actual sunrise and about 2 minutes after the actual sunset, and it all occurs due to the same phenomenon, which is atmospheric refraction. The apparent flattening of the sun's disk at sunrise and at sunset is also due to atmospheric refraction. So here is another animation which explains advanced sunrise and delayed sunset.
Atmospheric refraction.
Let us see it.
We've observed some natural phenomena in our daily life, such as the apparent random wavering or flickering of objects seen through a turbulent stream of hot air rising above a fire or a radiator. The twinkling of stars is a similar phenomenon. This wavering is thus an effect of atmospheric refraction, refraction of light by the Earth's atmosphere in our local environment. Let us discuss about them. Twinkling of stars. The twinkling of a star is due to atmospheric refraction of starlight. The scientific name for the twinkling of stars is stellar scintillation or astronomical scintillation. Stars twinkle when we see them from the Earth's surface because we are viewing them through thick layers of turbulent, moving air in the Earth's atmosphere. Stars, except for the sun, appear as tiny dots in the sky. As their light travels through the many layers of the Earth's atmosphere, the light of the star is bent, refracted many times, and in random directions. Light is bent when it hits a change in density, like a pocket of cold air or hot air. This random refraction results in the star winking out. It looks as though the star moves a bit, and our eye interprets this as twinkling. Stars closer to the horizon appear to twinkle more than stars that are overhead. This is because the light of stars near the horizon has to travel through more air than the light of stars overhead, and so is subject to more refraction. Also, planets do not usually twinkle because they are so close to us. They appear big enough that the twinkling is not noticeable, except when the air is extremely turbulent. Stars would not appear to twinkle if we viewed them from outer space or from a planet or moon that didn't have an atmosphere. Apparent position of sun. Because of atmospheric refraction, we do not see the sun or the stars in its true position except when it is directly overhead. As a ray of light from the sun enters Earth's atmospheric at B, it continuously bends towards the radius of the Earth. The ray of light will reach the observer at O, as if it had come in the direction AO instead of in its true direction BO. Consequently, we do not see the true position of the sun. It is due to atmospheric refraction that the sun is visible before actual sunrise and after actual sunset. Do you know this fact? The sun appears to rise 2 minutes before the actual rise, and it continues to be seen 2 minutes after it has actually set. Therefore, the day becomes longer by 4 minutes due to atmospheric refraction.
So this was an informative animation about the advanced sunrise and delayed sunset. Now let us move to another topic, that is scattering of light. When a beam of light passes through a colloidal solution, the path of the light becomes visible. And why does this becomes visible? Due to the scattering of light by the colloid particles, and this effect is known as Tyndall effect. In the same manner, Earth's atmosphere also contains different particles. It contains air molecules, water droplets, dust, smoke, etc. So when sunlight passes through the atmosphere, the path of the light becomes visible due to the scattering of light by these particles. The color of the scattered light depends upon the size of the scattering particles. Very fine particles scatter blue light, while the larger particles scatter different colors of light. Next example of scattering of light is the blue color of the sky. The color of the scattered light depends on the size of the scattering particles. Very fine particles scatter mainly blue light, while if the particle is of larger size, they will scatter light of longer wavelengths. And if the scattering particle has very large size, then the scattered light may even appear to be white. So when sunlight passes through the atmosphere, the fine particles present in the atmosphere scatter blue color more strongly than the red, and this is the reason why the sky appears blue. If in case the earth did not had any atmosphere, scattering of light would not have been possible and the sky would appear dark. And this is the reason why the sky appears dark at very high altitudes.
Tyndall effect.
Let us
Why does the sky appear blue?
which
Don't know
tells
the answer?
why the
No
sky
worries.
appears
We shall find the solution. It is such a beautiful rainbow. Have you ever wondered how it is formed? A rainbow is formed when raindrops split sunlight into different colors. Sunlight, or white light, consists of many colors. However, only a few of them are visible to us. A band of these visible colors is called a visible spectrum. When we see a rainbow, our brain and eyes distinguish the visible spectrum into 7 main colors, namely red, orange, yellow, green, blue, indigo, and violet.
Aha! Ah!
Hey, did you notice that the size of the balls increased? Yes, you guessed right. The balls represent the different colors of a rainbow in increasing order of their wavelengths. Wavelength is the distance between consecutive crests or consecutive troughs in a wave. In a rainbow, as we move from violet to red, the wavelength of colors increases. Violet has the shortest wavelength, while red has the longest wavelength. Do you think that our eyes have a natural inclination toward blue as compared to violet? Yes, this is one of the reasons why our sky appears blue and not violet. To understand this, first, let us study about Tyndall effect. Tyndall effect is a phenomenon in which a beam of light scatters on striking the particles present in its path. This scattering of light is responsible for the blue color of the sky. We know that our atmosphere primarily consists of oxygen and nitrogen particles, along with dust, smoke, and other particles in comparatively smaller proportions. The size of these particles in the atmosphere is responsible for the color of scattered light. When the sunlight strikes particles of dust, smoke, etc., which are bigger than the wavelength of sunlight, all the colors of sunlight are equally scattered. As a result, the scattered light appears white. However, when the sunlight strikes particles of oxygen and nitrogen, which are smaller than the wavelength of sunlight, the colors of sunlight having shorter wavelengths, that is, blue and violet, are much more scattered than colors having longer wavelengths. But our eyes are much more sensitive to blue color as compared to violet. Hence, the sky appears blue to us.